In continuation of our discussions in the class, actually I am just preparing this video so that you can verify the derivations you have done for flow of fluid in a circular conduit, horizontal circular conduit. And first thing is, you see, we had done it when we did it for Newtonian fluid, we got Hagen-Poiseuille's equation. So now we are talking about is what will happen when we are using power law fluid. Okay. So now actually to sum it up or to give a comparison with respect to your derivation of Hagen-Poiseuille's equation, flow arrangement is just the same. Only difference being that the fluid behavior, we are talking about that fluid which follows this particular pattern. Now here you just note is Vx, velocity in x direction, and we are talking about this velocity variation in the velocity with respect to radial position. Okay, so now you are advised to refer to the derivation that you had done for Hagen-Poiseuille's equation. So now we are skipping up actually. So for laminar flow as done in case of Newtonian fluid, tau Rx is equal to delta P by 2L into R. So now you see where you can obtain it, you just earlier derivations, you refer to earlier tasks. Okay, now we are now going to write it for non-Newtonian fluid. So for non-Newtonian fluid, delta P by 2L into R is equal to K minus dVx dr to the power n. This is n is the flow behavior index, and we know for Newtonian fluid it is 1. Okay, and K becomes mu. Okay, so then the manipulations actually are just showing, okay, just we can do for this what you call separation of variable. We can write like this: dVz dr is equal to this 1 upon n and r to the power 1 by n. So then we can integrate it. We will be getting this particular here there should be a integration notation. Then when we do this integration, this is constant, so this comes out simply, and only this is integrated, so that factor of n plus 1 by n is there. So power as well as in the denominator it comes, and this is the constant of integration. Now we'll have to talk about this boundary conditions. So here we are having a constant of integration, so we can eliminate by the application of boundary condition. Now Vx is equal to 0 at r is equal to r, means at these surfaces, okay, at the interface with the solid surface, the velocity is 0. So then what we get, C is this constant of integration equal to this particular term where r got replaced by capital R. Okay, so then when we substitute the expression for a, then after simplification we get this factor. You see, just the same thing. Now when we include a is, you see, the whole thing similar except the power is capital R to the power n plus 1. So this term and whatever is there for n, so they get combined. So while combined, since this was a negative term, so this is a negative sign will be there, whereas for a it will be a positive one. So r to the power n plus 1 by n into minus r to the power n plus 1 by n. So then we can take out this r to the power n plus 1 by n outside, and rest of the thing remaining same, multiplied by 1 minus r by r to n plus 1 by n. Now you see what happens. Vx is equal to V maximum at r is equal to 0. At the center, velocity is maximum. Therefore, V maximum is equal to r is equal to 0, means this term becomes 0. So V maximum is basically this part of this expression. Okay. So till now actually we have done half part of the task. Actually, see, we have obtained an expression for Vx, which is basically velocity in x direction at location r, radial position of r. Okay, Vx means at radial position of r. Now we are required to determine, so after we have got the expression for Vx, okay, we can estimate the value of V average. So value of V average is basically, you see, in the denominator it will be the cross sectional area, and in the numerator it will be the net amount of fluid flowing through the circular conduit. So which is basically, you see, V into a conduit which is of annular shape. Okay, so which actually flow area will be 2 pi r into thickness of it, that is delta r, and since we are writing in integration form, so it is dr. Okay, so then we can simplify it. 2 pi is getting cancelled. Okay, so 2 pi r, sorry, pi is getting cancelled, so then we get 2 by r square into 0 to r v into r dr. Okay, so then we can substitute the expression for v max from this here. Sorry, v, not v max. Okay, v, which is equal to v maximum multiplied by 1 minus r by r through the particular factor. So v is equal to v max into 1 minus r by r to the power particular n plus 1 by n, that factor, and then again r is there and dr. So now we are talking about this transformation of the variable. So r is getting transformed to y. So r is defined such that actually r is equal to capital R into y, which means r is equal to capital R dy. So therefore this limits also changes. So when r is equal to 0, this y value is 0, and when r is capital R, this y value is 1. Capital R by r means 1. Okay, therefore this V average is equal to means integration of V maximum divided r square, then this is y into r, one of the r here, it gives you the value of r, and y into dy, sorry, r into dy gives you the value of dr. Okay, so you can refer to earlier expression where it was a product of r into dr. So r into dr is now is y into r square dy, and this particular is term is 1 minus y to the power that particular factor n plus 1 by n. Okay, so then sorry, there is overwriting. So this is actually a factor of these two remaining, 2 multiplied by v maximum, then we are integrating it, we are getting this particular term. So by substitution of those limits, we get this equal to 2 times of v maximum into half minus n divided by 3n plus 1. So then we get, by cancelling simplification and then cancelling of the term like 2, and again you see this term becomes 3n plus 1 into 2. So these 2's are getting cancelled, then this is 2n, so it is n plus 1 divided by 3n plus 1. Okay, so now this is another objective, actually that is usually the second objective we talk about. Okay, so what is the expression for V average? Okay, so we are stopping, then we'll be moving to the next part of it, the calculation of pressure drop in case of this non-Newtonian fluid.